All right, it is now December 8th, day 8 of the Advent of Code 2020. We are going to live stream and record and maybe upload to YouTube video of me solving it in real time. You can experience what it's like to program computer for real from someone who has been doing it for a very long time. If you somehow stumbled upon this video and don't know what's going on, Advent of Code is an annual programming puzzle sort of competition thing. Every day from December 1st to December 25th, there's a new puzzle, and it's kind of hard to solve the puzzle unless you program the computer. You could theoretically solve it some other way, but computer is definitely almost always required. Um, and I'm going to solve it using the Python programming language that I am good with, right? So I heard the day 8 has is the first one this year that basically makes you write a computer processor, right? Process assembly language. We'll see if that is correct. Um, but yeah, that's always going to happen eventually in Advent of Code, I guess. I know how to do it, but we'll see if it's worth my time. Or, if you want to believe that that's a cop out, I'm too lazy, or I can't do it, you can believe that. All right, let's just go. All right, Advent of Code 2020, day 8. Handheld halting your flight to the major airline hub reaches cruising altitude without incident. Good. While you consider checking the in-flight menu for one of those drinks that come with an umbrella, you're interrupted by a kid standing next to you. Their handheld game console won't turn on. Oh no, you're in big trouble. That kid's, it's like, damn. They ask if you can take a look. I sure can. You know how the problem has a strange infinite loop in the boot code. The boot code is the puzzle input. You should be able to fix it, but first you need to run the code in isolation. The boot code is represented as a text file with one instruction per line. Oh yeah, we're doing assembly language, right? Of text, each instruction consists of an operation. There are 3 operations, right? Accumulate, jump, and no op. And one argument, a signed number like +4 or -20. Oh, it's always signed. That's interesting. ACC increases or decreases a single global value called the accumulator by the value given in the argument. For example, ACK +7 would increase the accumulator by 7. The accumulator starts at 0. All right. After an ACK instruction, the instruction immediately below it is executed next. Cool. Jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the jump instruction. For example, jump +2 would skip to the next instruction. Jump +1 would continue the instruction immediately below it. And jump -20 would go 20 lines above. Yep. So jump changes the program counter. No op stands for no operation. It does nothing. And so no op is the same as jump +1. They're the same exact thing, right? Because you're going to the instruction immediately below. The instruction immediately below is executed next. So jump +1 is no op. They're identical. Consider the following program. Do nothing, which means then accumulate +1. Accumulator is now 1. Jump +4. 1, 2, 3, 4. Accumulator +1 again. Accumulator is now 2. Jump -4. 1, 2, 3, 4. Accumulator +3. Accumulator is now 5. Jump -3. 1, 2, 3. Accumulator is now 6. Jump +4. That's an infinite loop because we've hit jump +4 before, right? The first no op does nothing. Then the accumulator is increased from 0 to 1. Jump 4 sets the next instruction to the other accumulator +1 to the bottom. After increasing the accumulator 1 to 2, jump -4. Accumulator +3. Accumulator 5, jump 3. Program it back to the first, ACK +1. There's an infinite loop. With this sequence of jumps, the program will run forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Yeah, so it's a computer science law that you basically can't tell if a program in like a full computer, in a complete computer, will be an infinite loop or not until you actually run it, right? So here we are running it to determine that But also, I don't think this is a complete computer necessarily because it only has one instruction. Maybe I know it's been a long time since I've checked the definitions of those things. Anyway, program run forever. The moment the program tries to run instruction, you know will never terminate. Immediately before the program would run an instruction a second time, the value in the accumulator is 5. Return your copy. Run your copy of the boot code immediately before any instruction is executed a second time. What value is in the accumulator? To begin, get your puzzle input. I know exactly how I'm going to solve this, but we'll see how long it takes to actually code it is the question. Save. All right, here we go. So we are going to start by, let's make this a little bigger. We'll take our puzzle input from yesterday, our code from yesterday. We're going to call it handheld halting. We'll move our input to input.text like I always do. Okay. Delete, delete, delete. Delete all that. Delete all that. And we'll just put that in there for now. Delete all this. There. Part 1, result equals something. Part 2, result equals something. We don't know yet. Okay, so I know exactly how I'm going to do this. We're actually going to make a second file for this, right? After I just clean up this file. Okay, we're going to make a second file now. And the file is going to be called handheld computer, right? Handheld game console, HGC, hgc.py, sure. Okay, here's our handheld, and then import HGC. Yeah, I know HGC is imported and never used because it's, you know. Okay, class HGC. All right, so we're gonna create here the HGC gaming device, right? So the HGC gaming device is going to have a program counter which starts equal to 0. And it's going to have an accumulator, which is also starts at 0. And boop, boop, boop. Okay. And then it's going to have a thing, execute program. You send it a program and it executes that program, right? And the program format is we're gonna define that later when we parse the input file. Let's actually take a look at that input file. Yep, it's just jump, ack, and nop, right? Okay. So what we're gonna do is we're gonna make a jump, a nop, and an ack function, right? Okay, we got 3 functions. All right. So if we, and it's going to be the param. It has 1 param, right? So, and this also has a param. And the nop has no param, just has self. And they all have self. Okay. So when the nop is called, all right, the nop function is the same thing as calling self. We already talked about this. Self.jump1, right, is the same exact thing as nop. Okay. Okay, if someone calls ack, self.accumulator plus equals param, right? And then self.jump1. Jump, right? What jump is going to do is self.program counter plus equals param. Right? So we have here our thing, right? And then execute program. So for instruction in program, for instruction, comma, param in program, right? We are going to up here, instruction set. It's going to be a dictionary, right? And our instruction set is going to be jump, right? Is going to be jump. Let's actually give these better names. Jump. No operation. Accumulate, right? Okay. So for jump, we're going to jump. For nop, no operation. And then accumulate. Okay. So for instruction param in program, we are going to do instruction set instruction, and then param. Maybe we can't put that there. We have, because self is not in scope. We have to put this inside the here instruction set. Okay, that's fine. Oh, forgot the self on the execute. Too many blank lines. Terrific. So we've just made a computer here. We just have to parse our instruction set, right? This is a whole computer with 3 assembly instructions you can execute. So let's go parse. I might make a test. I could make a test framework for this, but we're not going to do that right now. We're just going to go and let's parse the input. Right? Okay, so parse input file. We're trying to make a program. So the program is going to be a list. Okay. Oh wait. We don't just want to do this. This is wrong. We want to say while. Let's actually do this. Executed instructions. Right? So we want to say while true. We'll actually solve the problem here, I think. I was going to just leave it at generic computer, but we're going to solve the problem instead. We are going to do instruction param equals program self.program counter. Okay. So we're going to, so what this does is it's going to look for, it's going to go through the program listing. It's going to take the instruction and the param, right, from the current instruction. And then it's going to do instruction set instruction param. But the problem said right before executing the instruction, if it's already been instructed, we are going to, oops, we lost our thing here. This order. Immediately the value in the accumulator is what we want. What is the value is in the accumulator? Okay, so what we want to do is we want to say if, right? Okay. So, so before we run this instruction, right? So we want to say if self.program counter is in executed instructions, return self.accumulator and break. Well, we could just return, actually. That should bust us out of this, right? Or we could just say break and then return out here. We don't need this anymore, right? And so that's if we're about to execute something we've executed before, right? And if not, then we're going to execute the instruction, and then we are going to do executed instructions plus equals self.program counter. And then come back around. Okay. So this should work. All right, let's go back to parsing. All right. So for line in input file, read split lines. Okay, here's our program listing. Our instructions are going to be tuples. We're going to do, well, we can say for, we'll just say line, right? And then we'll do instruction param. Well, let's do some testing. Let's see. Nope, that's too tiny. Let's open the input over here. Okay, instruction equals ACK plus 42. Cool. Instruction dot split on a space, right? So instruction. I wonder if we can do instruction param equals IP. Yes, we can. Oop. We can do that. All right. So in that case, you want to say instruction param equals line dot split on space. We'll split that up. And then we have to clean up the param a little bit. So if param 0 is equal to the plus sign, then what we want to do is we want to actually say param equals param P1 colon? Yeah, 1 colon. 1 colon to remove that plus sign, and we want to make it integer, right? Else, param, oh, you know what? We can always say, oh no. Else param equals the same thing times -1. You can do that. This is, I guess we could have done, param string. Right, so if we can say param equals int, no, we can just do this, right? We're always doing that no matter what, and then we say if param string 0, if param string 0 is what's it called? Is equal to a the negative sign, then param times equals -1. All right, and that should parse out that integer there. Okay, that's unused still. Oh, param string. Cool. I know HTC. Leave me alone with that already. All right. All right, and now we are going to, we're going to do program append instruction param, right? And that should give us our program, return program. So we'll say program listing equals parse input file input.txt. And then we can now import HGC. Great. I know we're going to do HGC dot HGC to make a new computer. Okay. Computer equals HGC.HG handheld gaming computer, right? Or we can just say handheld game equals a new computer that's fresh, hasn't run it, just booted, right? We can even add like a reboot function if we want. We don't need this. I'll do that just for fun. We're going to boot the computer. And then we will execute the program, right? Handheld game.execute the program listing. And then the part, that's actually the part 1 result. That's actually the part 1 result right there. Okay. Let us run this and see what happens. Int object is not iterable. Plus equals self.program counter. All right. Which line is that? Executed instructions. Plus equals self.program counter. Executed. All right, let's just put a breakpoint here. See what happens. Cool. Self.program counter is 1. Of course, we're going straight to line 2, executed instructions. Okay, list plus equals self.program counter. Oh, we can't do that there. We have to instead do append. All right, that's fine. Let's remove our breakpoint. Now we can close our input now. All right. Execute again. We got 22. What I'm going to do is I want to make sure that this is, I'm going to take this listing instead, right? This test input. And we are going to verify the answer for this one should be 5, right? The value in the accumulator is 5. So with this instructions, we should get a 5. So I'm going to copy this. We're going to make a new test.text, right? Oops. We're going to copy this. We're going to paste it here. Okay. And now we should be able to change this input text to a test.text, right? And now if we run this, we should get 5. We did not. Takes 1 positional argument, but 2 were given. No operation takes a positional argument, but 2 were given. Okay. Let's see what's up there, see? Let's just put a break. You know what? Let's do this. Try type error. Accept type error as E. Breakpoint print E. Okay, E. Type error. Takes 1 positional argument, but 2 were given. Okay, instruction set is looking good. The instruction is NOP, and the param is 0. I see the problem. Nop doesn't take a param, right? What we want to do is down here on the nop, right? We just want to do args, and those are going to be thrown away, not considered, but at least it won't error. Okay. Part 1, 0. So that's not correct. All right, so our thing is not correct. But now we have a tiny, tiny input we can debug, right? So what we're going to do, we're going to print out the instruction, the counter, and the accumulator, and we're gonna and then we're gonna look at test.txt next to it. Okay, so and it has line numbers next to it, so that's good. Okay, cool. Every loop, right? Every time we execute an instruction, or before, I guess, we will print some stars. We don't need to do it on both ends. We're going to print the instruction, do f string. We will print the PC, self.program counter. Oh, the param. 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 Cool. Oh, we got to put this all underneath. All right, so the instruction, the param, the program counter, and the accumulator. Nice. And we might as well also print the executed instructions. Doesn't hurt. And then put a breakpoint. Cool. All right, so we get a no op. The program counter is 0. It's currently 0. No, the parameter is 0 on the no op. We don't care about it though. The program counter is now 1 because we've already executed the no op. It was 0. The accumulator is 0, and we have executed number 1. That's not correct. This needs to happen before we execute the instruction, because we just executed instruction 0. We didn't execute instruction 1. So that's a bug already we found. Okay, cool. All right, perfect. Now the no op has happened. So no op is the instruction. The parameter on the no op is 0, right? The program counter has become 1. It was 0, right? I guess we can do this. We can do can put these up here, and then put this under PC old, right? The old program counter, and then the new one, and then we can also do the same thing with the accumulator. The AC old and the AC new. Okay. Cool. So the program counter went from 0 to 1. Good. The accumulator went from 0 to 0, which it's a no op. That's correct. And we've executed program 0. Continue. Okay. The program counter was at 1. Yep. 1 to 1. Cool. We saying accumulate. Oh, the parameter is 1. Sorry. The parameter is 1. Accumulate 1. The program counter was 1, 1, 1. It's become 2. Good. That's correct. The accumulator has gone from 0 to 1, and we executed instruction 1. Very nice. Okay, we have now executed instruction 2. The accumulator, it's now a jump 4. Okay, cool. The program counter old was 2. It is now 6. 3, 4, 5, 6. Jump 4. 1, 2. See, we're here. 3. A 4. 1, 2, 3, 4. That's 6 because minus 1 because this doesn't start at 0. Okay, so the next program counter should be 6, and it should be the accumulate plus 1 should be the next instruction that we see, should be accumulate plus 1. And the accumulator is still 1 because we just executed a jump instruction which does not modify the accumulator. We now are seeing an accumulate plus 1. Yep, that is the correct next instruction. It is at program counter 6. We're now going to move to 7. The accumulator went from 1 to 2. Perfect. Next, we went to 7. A jump minus 4. All right, jump minus 4. It's 7, but now it's 3. We minus 4'd from the program counter. The accumulator has not modified. Continue. We are now at number 3, right? Another new instruction here, which is the, it's this one. It's accumulate plus 3. Minus 1 over there. All right, okay, so the accumulator went up by 3. The program counter now goes to the next one, which is the jump minus 3. Yep, okay, so that was instruction 4. The jump minus 3 is going to set the program counter to 1 for the next instruction, which is going to be the end. And we got 5. That we fixed our bug. That bug was what was giving us the wrong answer. We are now getting the right answer. So thanks to that, we can now switch back to input.txt. And we are pretty confident that this is going to work. Oh, we can remove all our debugging codes. Oh, not that one, though. All right, I think what we can do is I think we can make an HGC, like a separate unit test for the HGC computer. Rather than putting the debugging statements like inside the HGC, and that way we can run the test separately, which we will do. Okay. Handheld halting. The answer is 1782. That looks like a right answer to me. Let's go type it in. 1782. That's the right answer. Oh, yeah. That's right. We made a whole computer in 30 minutes. How about that? A 3-instruction computer. All right. Part 2. Please don't be that divergent from part 1. I don't want to sit here all night. Okay. After some careful analysis that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a nop or a nop is supposed to be a jump. No acts were harmed in the correction of this boot code. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or nop, you can repair the boot code and make it terminate correctly. Uh-oh. This might be a toughie. For example, consider the same program from above. Okay, it's the same program from above. If we change the first instruction from nop 0 to jump 0, it would create a single instruction infinite loop. That's correct. Never leaving that instruction. Yep. If you change almost any of the jumps, the program will still eventually find another jump and loop forever. However, if you change the second to last instruction from jump minus 4 to not minus 4, you'll be able to reach this end point. All right, 1, 2, 3, 4, 5, 6. After the last instruction 6, then it's going to terminate. It's going to go to, right? It's going to go +1, which is going to go off the end of the file. With this change, after the program terminates, the accumulator contains the value 8. Fix the program so that it terminates normally by changing exactly one jump to nop or nop to jump. Oh boy, what is the value of the accumulator after the program terminates? Well, I'm actually don't know there's probably some clever way to do this part. Let's see if we can figure out which instruction is the one So we want to say while program counter is... All right, so termination means leaving, the program counter goes outside of the execute instructions, right? So, or the instructions, the program. So program equals like, you know, A, B, C. The length of P is going to be 3. So, but the program counter is 0, 1, 2. So when the program counter is equal to the length of the program, when the program while the program is less than the length of the program, continue to execute, and then when it busts out, right? Then we have achieved our result. Okay. All right. So that hasn't really, that's fine. Okay. So let's make another thing here. We want to repair the program first. Huh. So we want to get to 611 somehow. There must be some clever solution to this. Okay. It's probably a clever answer that I don't know. We could brute force it. You could go through, right? Well, first of all, let's see if there's any NOPs with non-zeros after them, right? Let's take a look at our input. NOP. Oh, yeah, there's a lot of NOPs that don't have zeros after them, right? Oh, hold the phone now, right? The final instruction, hold on, is a jump plus 1 is 611, which is actually 610, right? 610 is also okay, because let's go boop, 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 that'll end. This is a NOP, so if we land on 609, we'll also end, right? So what we want to do is we want to go through the whole program, right? And we're going to go to each jump, right? If we hit a jump, right, we're just going to go through the program from top to bottom. And then if we hit a jump, right, we're going to switch it to a NOP. Then we're going to execute that new program and say, does it complete or does it loop? No, because computer science, if it loops, there's no way to know. Oh, we'll know that it loops because we're assuming that the repeat of a single instruction is a loop. So here's what we can do. All right. So here, if we break, right, if we break here, we're breaking, then we're returning the accumulator. Instead, we can go return fail self.accumulator, just right in there. And then part one, and part, worked. Part one is all right. Looped. All right. Did loop. Okay, so I just want to try running part one again just to make sure. Cannot unpack non-iterable int program listing. We'll do while. We'll just switch this back to while true for a second. So if the program counter is in the executed instruction, return fail. Oh, so did loop actually? Oh, this is why. Did loop. And then part 1 result. Oh, fail is not ident. Yeah, what am I doing? Just fail. False. That's a failure. Oh, well, the completed. False. It didn't complete. 1782. Was that the right answer that we typed in before? I don't remember. I feel like it is. Anyway. Sure. And then, but if self.program counter is equal to the length of the program, we're going to return true. Accumulator. Right? We're going to do def set. Return true self.accumulator. And I don't know if we need this. I don't know if we need these breaks after these returns, but okay. Okay. If you change the first intro, I just want to make sure, is it possible to like go way off the end, right? Like what if there's like here, what if there's like a jump 20 that sends you off the end? Does that count as successful termination, right? Not supposed to see a jump. That looks like, okay, the program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file, right? So jumping way off the end is not correct. So we want to say if the program counter, is exactly equal to the length of the program, we found our answer. Okay, so now what we're going to do is we're going to take our fixed program, right? We're going to take our program listing. Okay, we're going to say the original listing. We're going to make a copy of it, right? So what we want to do is we want to say, just do some Googling. Python copy. Shallow and deep copy operations. Just import copy X, right? Okay. Cool. Original listing equals copy.copy program listing. We can say let's do this. Okay. Then we got attempted fixes equals this list, right? For instruction in the temp listing, well, hold on. I think we might use the Python Enumerator here. I just want to, remember how it works. A, B, C. right? Y for X, Y, and yep, that's correct. So for uh, 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 line number instruction in enumerate the temp listing, we are going to for line number instruction in enumerate if the instruction is going to be jump, not, or no, the instruction is going to have instruction and param, right? We'll say command param equals instruction. If instruction, if the first part of the instruction is in nop or jump, so if it's one of these two, make a flipper. Make a flipper here. Nop, jump, jump, nop. Okay. Actually, I don't think we need this attempted fixes or this enumeration. Which means we don't need the temp listing either. Because we can just flip back. If instruction 0 for the line number in the original, in the program listing, right? I just want to test this to be sure. Listing equals nop 5 jump -3. What? Oh. Okay, listing. So for, oh, we don't need the line number either anymore. Oh, we can do for instruction param. For instruction param in listing, right? Listing. Oops. Listing. Oh, maybe we do need the counter. Yeah, you know what? We'll do the copying anyway. I don't know it's necessary, but I'm going to do it just because. So for line no instruction, command param equals instruction. Yeah, I don't. If I do it this way, I just know it's going to work. If the command not in flipper, just continue, right? Because that's obviously just like in X. We don't need to change that one. Otherwise, we are going to say new listing equals copy of the program listing. Copy it. I'm pretty sure there's a clever way that's not this brute force way, but I don't know that way. So this is the way I'm going to do. Okay, we're going to copy the whole listing. We're going to take the new listing and that line number equal to the flipper command comma the param. So we're going to, replace that one instruction. Wait, I don't want that. All right, replace the one instruction. Make a new HGC. All right, make a new HGC. HGC dot, we're going to execute the new listing, right? And it's going to be completed part 2 result. If completed, return part 2 result. And I don't know, we don't need this break, but I'm doing it anyway. Don't think we need these breaks. I'm going to try it without the, right? Let's remove them. Because we have return. We don't need break if we have return. Pretty sure. All right. So if it's completed, right, return. Otherwise, we're going to go back to our original thing here, right? With another. Okay, so part 2 result equals fix program program listing. Handheld game. Oh. All right, let's see what happens. Thankfully, even though this is an inefficient brute force program, I have a very fast real world computer. List index out of range. Aha. So changing one of the instructions must have sent it way outside of the program. So we're going to say if self-up program counter is greater than the length of the program, right? We're going to, it won't error until we get down to here where we're actually trying to execute the instruction. We're going to return false. Oh, greater than the list in the program. Okay. And then I guess we'll also really it's just this. If it's equal to the length of the program, then we're successful. Otherwise, not. Right? If it's equal to the length of the program, do this. If it's in the executed instructions, do this. Oh, wait. Else. No, because we've got to set, there's still valid LF, it's if it's either less than 0 or self-up program counter is less than 0. Oh, program counter less than 0. Oh, we'll do counter low equals self-type program counter at less than 0. Counter high is a program counter greater than length of the program. Elif counter low or counter high. Return false as well. Okay. List index out of range still. Instruction param equals program. Line 20. Program counter. List index out of range. All right. Index error. Okay, index, list error out of range. What's our param, our instruction, program, counter, length of the program? Oh, I think we're onto something. I think we may have found the fix because we've landed at the end of our program, but our thing down here is failing. Instruction param equals program self. Aha! We have to check up there. We're checking down here. Right? Because what's happening is we've pulled our next instruction out in this loop. So I think what we actually want to do is we want to say while self-up program counter is not equal to the length of the program. And then we could do this. And then if we break out, hold on. Read it. Okay. So I do think we want to say this. While the self-up program counter is not equal to the length of the program. Okay. No. Is greater than 0 and self. Zero is less than or equal, and the counter and the is less than the length of the program. Yep. Okay. So then if we bust out of the loop, right, we can say if self-up program counter is equal to the length of the program, then we're going to return the true because we found a successful fix. And else, we're going to return, let's return none, right? Indicating out of bounds. Let's do that. We got an answer. We did get an answer. Wow. I'm just typing it in. I'm typing it in. I don't care. 797. Let's type it. That's the right answer. We done it. We done it. It actually took more time yesterday to parse some file than today to make a computer. Okay, where we go. 1 hour. Very nice. This might go to YouTube, I think. But yeah, now you see, right, how to basically make a computer, right? This is how, if you're making a chip, right? It's like, yeah, there's transistors and stuff that underlie all of this logic, but when you're coding in assembly, right? This is what's on the other end of your assembly code, something code that looks like this. Um, and if you're writing an emulator, right? Say for like, I don't know, a Nintendo or some other, microchip, right? You figure out, oh, okay, that microchip has what? It has, this many registers. So you create in your software space to hold the data that would be in those registers, right? Like we had space for the accumulator and the program counter. And then, you create a function for each instruction in the assembly language instruction set. And you start your program counter usually at 0. And you read the assembly instructions one at a time into memory. You hold them there. And then you move your program counter around, right, accordingly. And whatever the current program counter is, right, you get back to the top of your loop. You read that instruction and figure out which function matches to it. And then you modify all your program counter and your other in-memory data accordingly to the instruction. And then you look at the program counter and do it again and again and again and again. And that's how computers do. So we made a computer this is the other side, right? We're not writing in assembly, we're reading assembly and executing it. And it works, right? So yeah, don't feel like, that sort of world of computing is, sort of impossibly hard and inaccessible, right? If you're just starting out or, not the strongest programmer in the world, right? It's like, look, took me an hour, right? There were only 3 instructions, right? But all that's really different when you're doing, something real worldy is there's just a lot more instructions and a lot more possible parameters and things like that. Some of the instructions might be more difficult to implement than others, but this code is also extremely testable. I didn't spend time to write a testing framework, though I'm presuming this code is going to be reused on the coming days, in which case I am going to develop a custom testing, not a custom one, but I'll make a unit testing suite for the virtual computer, so that I know that it's always working properly and such. All right, so that was day 8 of the advent of code. We're on our way. If you enjoyed watching this or got anything out of it, I'm glad. You can come watch me do this live. You can watch it on YouTube. You can check the description for more info. I got links to the GitHub. You can check out my source code and have a grand old time. All right, we'll probably see you tomorrow because this still has only taken 1 hour. When it starts to take too long, I think we might stop, at least with the YouTube. Maybe not with the streaming. We'll see. Okay, have a great whatever time it is where you are now.